Okay, I'm sure my screen is visible to you. Chris, can you respond whether my screen is visible to you?
Yes, sir, it's visible.
Thank you, Chris. Yeah. So Diffie-Hellman key exchange will be our topic today for the short discussion. A little bit about Diffie-Hellman before we get into the actual technical details. What's the objective of Diffie-Hellman key exchange algorithm or method? It is to enable two users, okay, two entities, probably senders and the receiver, to securely exchange a key, all right, so which can be used later for the symmetric encryption of messages. At this time, I request you to recall one of the statements we have used to describe the public key crypto system. A public key crypto system is not going to replace the symmetric key algorithm or symmetric key crypto system, but rather it would augment the symmetric key crypto system, which means the public key crypto system is going to support the symmetric crypto system in a larger way, right? So now we got one of the lines, that the first line, which helps you, to substantiate that statement. It says to enable two users to securely exchange a key. Don't you remember that in the symmetric algorithm, the primary expectation is that the key has to be shared securely. Okay, the shared key, that is the secret key, has to be shared securely between two entities. How can we do that? We said it should be sent through a secure channel. Where do we have such secure channel existing? Yeah, this is one of the ways, right? Exchange a key that can be used for subsequent other symmetric, other encryption process. Second point about Diffie-Hellman is the effectiveness, the strength of Diffie-Hellman is depending on the discrete logarithm. You can ask a question, what is a discrete logarithm? For the people who are very much interested in mathematics, I encourage you to read the second chapter, if I am right, in our textbook, in our cryptography and network security textbook, which has given the full details of discrete logarithms. So the discussion of discrete logarithm is out of the scope of our regular class. However, we can discuss about that offline if anyone of you are interested about that. All right, moving on. But we should know what is a discrete logarithm, right? So probably this slide will help you to understand that in a little bit way before we proceed to actual Diffie-Hellman key exchange algorithm. What's happening here? We come across a word called primitive root. Okay, what is that primitive root? It's a new term. Yes, it's a new term for many of us. And I also have given the description to you what it is exactly. A primitive root of a prime number. Root of a prime number? Yes, we have got primitive root of a prime number. I have used the word small p. Okay, primitive root of a prime number p is the one. Okay, what is that root? Is the one whose powers. Okay, for example, if a is the primitive root, so a power 1, a power 2, a power 3, and so on, okay, whose powers modulus p will generate all the numbers from 1 to p minus 1. If I put a random number, for instance, if the primitive root of 10, okay, just for example, I'm saying, okay, prime number 11. Okay, the primitive root of prime number 11 is the one whose power modulo 11 will generate all the integers from 1 to 10. Okay, for example, a p power 0, then p power 1, the primitive root, if it is a power 0, a power 1, a power 2, up to, if you take the number, it will generate all the integer from 1 to 10. That is, if a is the primitive root of the prime number p, then the numbers a mod p, a power, no, a square mod p, then a cube, then a power 4, a power 5, up to a power p minus 1 mod p will give numbers, right? Those numbers, if you put them in the ascending order, you will get 1 to p minus 1, okay, are distinct and consist of all the integers from 1 to p minus 1, but some in some permutation. It may not be in the proper order. That's why I said we should go for ascending order. If you arrange them in a specific ascending order, you will be wondering to see all the numbers from 1 to p minus 1 existing. If p is 11 for our example, you will get a mod 11, a square mod 11, a cube mod 11, up to a power 10 mod 11. will give you all the numbers from 1 to 10, maybe in a jumbled way. Okay, what is that A? That is the primitive root. Okay, how can you find that? Using the discrete logarithm. All right. How can you find the A is out of the scope, but we need to learn about the discrete logarithm. Moving on, let's see how the algorithm works. But algorithm is very simple for you to understand. And I would also recommend you to use the correct notations. Otherwise, it will confuse you. You should not be confused. All right. So we take two entities, Alice and Bob. Okay, these are the two people on left hand side and right hand side. Their objective is to exchange a secret key. Can we use Diffie-Hellman key exchange algorithm? Yes, sir. You can use Diffie-Hellman key exchange algorithm to exchange the secret key. Okay, how it works? All right. So we'll look at the first step. First step is same to both. I read for you. Alice and Bob share a prime number q. Okay, so they take a prime number, and it is denoted as q here. All right, and an integer alpha. What is that alpha? Alpha is the primitive root of q. Okay, that's what I have spoken. What this alpha is. Okay, so they choose two numbers. One is q, and they also find the alpha such that alpha is obviously less than q, and it is a primitive root of q. What's happening? Both of them are doing the same thing. How are they doing? They may use some KDC. They may use when they are meeting each other. They would have shared this p and q. All right, let's leave that to them. But alpha and q are known to both the entities, sending as well as receiver. In our case, Alice and Bob, they both have the q and alpha with them. Both are same values. All right. What's the next step? Look at the left hand side. Alice generates a private key XA such that XA is less than Q. It's not generating, he creates a private key. Okay, he chooses a private key and such that the value should be less than Q. If your value of Q is 11, probably 10 or 8 or 9 or something like that. All right, so Alice takes a private key XA such that XA is less than Q. Remember, XA is the private key. Okay. But at the same time, what Bob is doing, Bob generates a private key XB such that XB is less than Q. By something like a birthday paradox. If you do not know, Google it up and find out what is birthday paradox. Okay. With the logic of birthday paradox, there is a possibility that XA may be equal to XB because they both choose this number independently. There could be a collision. Okay, there could be the number could be same, need not be same, but they only know what they have chosen. So XA and XB are the private keys of Alice and Bob respectively. Okay, now Alice calculates the public key. Okay, so he has to calculate the public key. How does he calculate? He calculates the public key, which is denoted as YA. Okay, XA is the private key of Alice. YA is the public key of Alice. Please remember that. So YA is alpha power XA mod Q. Isn't it simple? What is that alpha? The primitive root which you have chosen. XA is your private key. Mod Q, Q is the number which you have chosen as the a prime number initially. All right. So Alice generates a private key XA such that XA is less than Q. Okay. XA is less than Q. At the same time, what? Just hold on. Okay. At the same time, what Bob is doing, he also chooses, calculates the private public key YB, okay, such that alpha power XB mod Q is the formula. So what has happened so far? Two people, Alice and Bob, they have chosen Q, which is a common value. They also have calculated the alpha, which is the primitive root, done. Next step, they choose the private key, which is termed as XA for Alice, XB for Bob, and only condition it should be less than Q. Prime, not prime, but it should be integer. All right, it cannot be a fractional number. And then Alice and Bob simultaneously or parallelly they calculate the public key separately. Okay, Alice is doing from his house and Bob is calculating from his office. Okay, so what is that? YA is the public key of Alice. He is calculating using the formula alpha power XA mod Q. All right. Similarly, he is calculating the public key Bob alpha power XB mod Q. Okay. Now XA and XB are the private keys of Alice and Bob respectively. At the same time, YA and YB are the public key of Alice and Bob respectively. Being a public key, YA and YB are exchanged. You got it? They're exchanged. Okay. Now what happens? Alice receives Bob's public key. Yeah, because it is exchanged from him. Similarly, Bob receives Alice's public key. There is a keyword given on the screen. You can denote. It says it is. I'll use the pen. Okay. It says it is in plain text. Okay. So this you should remember. It is in plain text. We should the word plain text comes here. It is not encrypted. It's a number which is calculated. The public value is just thrown. Okay, sent across through a postcard, for instance. It's going as a plain text. Is it all over? No, sir. What has happened so far? They both have generated the private keys and public key pair. That's all has happened. Okay, how are we going to exchange the secret key? Because at the start of the session I said Diffie-Hellman key exchange algorithm is going to help you to exchange the secret key. Where is it happening? Yes, it's happening in the last step. Look at the last step. Now Alice calculates the secret key K by using the formula YB power XA. Okay, you can easily remember this formula. Here the power XA mod Q, here also power XA mod Q. Instead of alpha, you will have YB. YB is the public key of the other side, Bob here. So YB power XA mod Q. Obviously, the other person will calculate K such that YA power XB mod Q, because he uses his public key in the power and then mod Q. So what? Now, interestingly, K equal to okay, K equal to YB power XA mod Q is equal to K equal to YA power XB mod Q. I'll try whether I can explain this. So suppose you go for a calculation. What is YB power XA mod Q? What is YB? Where is YB? YB is alpha power XP mod Q. Okay, so YB is alpha power XP mod Q, and then power XA mod Q. I'm sorry for the poor handwriting, but please bear with me. What have I done? Instead of YB, I have replaced this formula alpha power XB mod Q. Okay, so I put alpha power XB mod Q power XA mod Q. This is equal to K. Hope you agree with my calculation. So what happens after that? Alpha power XB mod Q power XA mod Q is similar to alpha power XB XA mod Q. We know, no, taking the modulus of the numbers and then multiply and then take the modulus is equal to multiplying and then take the modulus. So alpha power XB mod Q power XA mod Q is equal to alpha power XB power x alpha power XB multiplied by XA then mod Q. All right. XB XA can be swapped. Okay. So what will happen in the next step? It will become alpha power XA XB mod Q. Let me see whether I can write alpha power XA and then XB here. Okay. And then mod Q. So how can this be written? This can be written alpha power XA mod Q power XP. Okay, like this instead of XP. So let me try alpha power XA mod Q, and I can take XB mod Q. Okay, alpha power XA mod Q. Where is it? Alpha power XA mod Q is YA. So this is equal to YA power XB mod Q. Okay, YA power XB mod Q. Where is YA power XB mod Q? It is here. Okay, YA power XB mod Q. So I started here. Okay, and I end up showing that this is equal to 6, which indicates that the K which is generated by the person called Alice is equal to the value K which is generated by Bob. Please forgive me for my poor handwriting, but This is how. Okay. So K is equal to YB power XA mod Q. This is the key which is generated. What have I done? YB I have replaced with alpha power XB mod Q. Okay. Alpha power XB mod Q. And then what have I done? I'm sorry. So that I have taken, I have replaced it. YB is replaced by alpha power XB mod Q. Then I have just brought in the XA inside. Okay, then XB XA. Then I swapped XA XB. I brought the XB outside. So I will get alpha power. Where is it? Is here. Okay, alpha power XA mod Q, then XB mod Q. This is equal to YA. You got it here. This is equal to YA. So YA power XB mod Q is equal to K. This is just a proof that the K value which is generated by Alice and the K value which is generated by Bob are equal. All right. What have we achieved, sir? Don't you think at the end of the day a key value which is generated at the both the side, both are equal? This is what our objective. You have shared a secret key called K. Now this K is the value which is called the secret key, can be used for your symmetric key crypto system. For instance, your AES or DES, they all use symmetric key crypto systems, right? So it can be used for the symmetric key crypto system for further encryption, decryption process. Okay, this is what the whole thing of your Diffie-Hellman key exchange algorithm. So Diffie-Hellman key exchange algorithm, is it used to share any message? Not directly. Okay, it is used to share a key because we do not know what key is generated, but whatever is generated both the side will be same. That is the only assurance which we have got. All right. So quickly to recall, we got Alice and Bob, two people here. Okay, objective is to share a secret key using the Diffie-Hellman key exchange algorithm. Both of them choose a primary key, prime number Q, and also a primitive root of Q alpha such that alpha is less than Q. First step. Then parallelly, but at different locations, they choose a private key which is less than Q. All right. Then they calculate the public key separately, parallelly but separately at different location. They calculate the public key. Public key is shared across them, and then based on the shared public key, secret key is calculated by using the formula. And we also found that these two keys are equal. Key is shared, secret key is shared. All right, that's it. Okay, so this is an example. If you have understood what we have spoken earlier, this is simple. So both of them share a prime number called Q. We had taken the value as 353, and the primitive root of 353 alpha is 3. So how can you find out? Using the logarithmic arithmetic. Okay, then A and B. A and B are Alice and Bob. Select private keys. Okay, in this example, Alice chooses the private key as XA and Bob chooses the private key as XB. 97 and 233 both are less than 353. Okay, respectively. Then public key they are supposed to calculate. So person A computes the public key YA such that alpha power XA, alpha is 3, XA is 97. 3 power 97 mod Q, Q is 353. He calculates it at 40. B computes the public key and he has arrived at 248. Now 40 and 248 are exchanged. Okay, which means this is YA, this is YB. Now A computes the secret key by using the formula YB power XA mod 353. YB power mod XA mod 53. In this example, it comes as this one. You will end up in getting 160. Similarly, parallelly, the other person also computes. He also ends up in getting 160. Now, 160 is the secret key, which is shared between A and B, sender and the receiver, Alice and Bob, by using Diffie-Hellman key exchange algorithm, right? Okay, and if you remember in the diagram which we had in the previous case, we saw a line that public key YB is in plain text. I also told you to remember this word plain text. Okay, why should I? Yeah. Now the problem here is your Diffie-Hellman key exchange algorithm is vulnerable to man-in-the-middle attack. If you have forgotten what is that man-in-the-middle attack, between the sender and the receiver, the third person, like a dart or the attacker comes in and he is doing a foul play. Okay, he sits in the middle, maybe involved in active attack, he may be involved in passive attack as well. Okay, he can modify the message, he can replay the message, he can no, receive the message and swallow it so that it will not be received by the other side. He can do multiple mischievous things. Okay, now whether our Diffie-Hellman is vulnerable, unfortunately, Diffie-Hellman key exchange methodology or algorithm is vulnerable to man-in-the-middle attack. How is it possible? You can look at the diagram. It helps you to understand that. Don't worry about the diagram. It looks some complicated. That is nothing complicated. Very simple to understand. Look at that. I'll explain to you. First step. Okay. Alice chooses the private key, he calculates the public key. Isn't it different? No. Is it same like this? He chooses the private key, he calculates the public key. So far, no problem. Okay. At the same time, Bob also chooses the private key, he also chooses the public key. This and this has no problem, sir. Absolute no problem. Okay. And then look at Alice, he exchanges the public key with the other side. Okay, what is that other side? He's thinking that he's sending to Bob. Okay, he has sent it, maybe over using a postcard or using an email. Somehow he has sent it. Now there is a person called Darth. He's a bad fellow. Okay, he's sitting in the middle. He receives this message. All right, and also he makes sure that this message does not go to Bob. Man in the middle attack. All right, now what he is doing at the same time, he chooses two private keys. They are named as, instead of XA attacker, so XD1, D stands for dot here. So he creates chooses two private keys, XD1 and XD2. He calculates two public keys, okay, YD1 and YD2. And what he is doing, after receiving this XA, he stops that from going that side. He meticulously plans and he sends one of the public keys here, YD2. Now Alice thinks that this is the key he has received from Bob. Something fishy, right? Yeah. Similarly, he is sending another public key to this Bob side. Bob thinks that he has received this public key from Alice. What's the problem? Because the messages are exchanged as a plain text. There is absolutely no authentication. Okay. Now Alice and Bob think that they have received the public key from the corresponding person from the other side. Alice thinks he has got from Bob. Bob thinks he has got it from Alice. But in reality, they have received the public key from Darth. Okay, let's look at the play. What happens? Then Alice creates. Oh, I'm sorry. Alice calculates the private key. Secret key. How is he creating the secret key? By using, earlier it was YB power XA mod Q. Here it is YD2 power XA mod Q. And he also does the same thing, YD1 power XB mod Q. And look at Darth, what he is doing. He has chosen, he has calculated two secret keys. One is K2. K2 is calculated by YA. What is YA? His public key. Power XD2. What is XD2? His own private key, what he has chosen. Okay, YA power XD2 mod Q. He got key called K2. Okay, who has got K2? YD2, which means person called Alice also has got K2. You can easily prove that these two are same. Okay, how will you do that? Very simple. YD2, how YD2 is calculated? Alpha power XD2. So alpha power XD2 power XA mod Q, which means alpha power XA mod Q power XD2, which is equal to YA. All right. Alpha over XA mod equal to YA power X2. So these two are same. K2 is equal to K2. K1 is equal to K1. Now what has happened? Alice and Bob are thinking that they have exchanged a secret key between them. Alice thinks that he has shared a key with Bob. Bob thinks that he has shared a key with Alice. But in reality, because of the man in the middle attack, and also because the keys are exchanged as a plain text, what has happened? Alice has shared a key with Darth, and Bob has shared a key with Darth. Alice may be using this key tomorrow to share a message with Bob using the symmetric algorithm, thinking that he is having the key, but in practical here, the key is with Darth. Alice does not know, and the poor Bob also does not know. But they are thinking that they have shared the key secretly, but in fact, they have shared the key with the attacker. Total of your Diffie-Hellman key exchange is compromised. All right. Why? Alice and Darth have shared the key called K2. Bob and Darth have shared a key called K1. Okay. So, Diffie-Hellman key exchange algorithm is vulnerable to man-in-the-middle attack. Right. So this is what your Diffie-Hellman key exchange algorithm. Quickly to recall before winding up the session, Alice and Bob, they choose two values. One is the prime number, and another value is alpha, which is the primitive root of this prime number q. Obviously, it should be less than q. And then they choose a private key called xa and xb respectively. Only condition is it should be an integer less than q, and then they calculate the public keys. Okay, so ya is calculated, yb is calculated. Ya is alpha per xa mod q, yb is alpha per ya mod alpha per xp mod q, yb. Okay, they exchange the secret key ya and yb across them, and that's the last the penultimate step. In the final step, they calculate the secret key. Okay, key is yb power xa mod q. Here it is ya power xp mod q. Isn't it simple? They have shared a key. All right, this key can be used for any further symmetric key encryption. We also found some vulnerability here, that it is vulnerable to man-in-the-middle attack, and I also have shown you, of course I have borrowed this from your textbook, but I have shown you how man-in-the-middle attack can compromise your Diffie-Hellman key exchange algorithm completely. The reason is Alice and Bob till now do not know that their keys are compromised. They have shared a key with the attacker, which is very, very dangerous. All right. Right. That's it. So that's all from me. And